All right, so we are almost done. We've got two major theorems to go. We've done a couple of major theorems in this particular chapter. We've already done the fundamental theorem for line integrals, and we've done Green's theorem. We still have Stokes' theorem, which we'll talk about today, and then we have the divergence theorem, which is the next and last lesson that we will do. The good thing here about Stokes' theorem is it has a direct relationship to Green's theorem. So if you understood Green's theorem, at least this is going to be something that you will be able to at least relate to. So let's go ahead and take a look here at what Stokes' theorem says. So first of all, let's go back actually. So I said it directly relates to Green's theorem. So it has a directly relates to Green's theorem. And so if you recall what Green's theorem was, excuse me, the Green's theorem says if you were to take the line integral of f dot dr, you could do that by doing the double integral over d of dq dx, so the partial of q with respect to x, minus dp dy, partial of p with respect to y, dA. Okay, and this was something that was really good because what it did is it made line integrals over closed regions easier to do, this double integral. So let's say, for example, that we had just some easy region here to deal with. Just say we had some kind of a rectangular or square box or something like that. And I wanted to find the line integral over that specific region. Well, if we did the line integral, first of all, you would have to do, C1, C2, C3, and C4. We'd have to do 4 separate line integrals to get this thing. Well, Green's theorem said, well, okay, if we can traverse this thing in a counterclockwise fashion, we can go maybe, this way, all the way around this thing, then we can use Green's theorem to find the line integral. Instead of doing the line integral in 4 separate parts, we just have to do the double integral of dq dx minus dp dy. Not really that difficult to do. It made things much easier actually, but the downside to this was this only worked if your vector field was a two-dimensional curve. So I guess you could say this only works if f of your P and Q was a two-dimensional curve of some kind. So basically that thing had to be sitting flat, like on an xy plane or on the xz plane or something like that. Just had to be a two-dimensional curve. Well, the nice thing is that Stokes' theorem basically takes this idea of Green's theorem and extends it to a three-dimensional curve or a three-dimensional surface. So let's take a look at what Stokes' theorem actually says. So again, Stokes' theorem, Stokes extends the idea of Green's theorem to 3D. So what it says, what Stokes' theorem says, is if you have some kind of a surface. So Stokes says if S is an oriented surface, which is counterclockwise, that's what the oriented means, bounded by the curve C, which is, here we go, positively oriented, or positively closed. So it's a positively oriented surface. The curve C is going to be positively oriented, and the curve has to be closed, just like Green's theorem has to be a closed surface. It can't be something open. Can't be like I'm going to erase this, but you can't have a surface which does this and stops. Okay, it somehow has to have a curve which is closed underneath of your surface or above your surface or whatever. So that has to be the case. If that's the case, then what we can do is we can take the curl, we can take the line integral, I'm getting ahead of myself, of f dot dr over that line integral C, and we can figure that out by doing the double integral of the surface of the curl of f dotted with ds. Okay, and what we're going to do is we're going to actually talk about why this is after we get through example 2 and try and get a little more into the concept. I am going to basically try and explain as we look at the first example what's actually happening here a little bit. But this is the general idea. It says that I can use the line integral of f dot dr over some kind of a curve, and I can do the double integral of the surface of the curl dotted with ds, and you can go either way. Okay, so we're going to go ahead and take a look at a few examples. These examples can get a little bit long, so it'll probably be about one example per video. Okay, our first example says evaluate the line integral of f dot dr where the vector field is given by negative y squared I plus xj plus z squared k, and C is the curve of the intersection of the plane y plus z equals 2 and the cylinder x squared plus y squared equals 1. Orient C to be counterclockwise when viewed from above. So the sketch over here kind of shows us what we're looking at. You've got your plane which is slicing that cylinder at some kind of an angle. And then what you have here, and it actually has it drawn on there. It's kind of hard to see, so I'm going to go ahead and sketch right over top of it here. But this right here, this is your curve, and there are little arrows. Boy, that was horrible. I probably should have just left it alone, but there were little arrows on there showing that this thing is as viewed from above. So if you were looking straight down on it, it is going to have a counterclockwise rotation. Alright, so it says to evaluate f dot dr. Now you could do this, or you could potentially do this by doing f dot dr as it is. You could do the line integral of this thing, and it would not be an incorrect way to do it. But what we're going to do is we're going to use Stokes Theorem here to figure this thing out. So what Stokes Theorem again says was that the line integral over C of f dotted with dr is the same thing as the double integral over S of the curl of f dotted with ds. Now if you remember, the ds part, well, I'm going to write this up above here, ds is defined to be Rx cross Ry, or Ru cross Rv, or R theta cross R, or whatever the variables happen to be after you parameterized it. It's the cross product, and because it's the cross product, we know that to be the normal vector, so I'm going to call it the normal vector, and then dA. So that's what the ds part actually is. So I actually prefer to write it in this fashion myself, just because it tells me exactly what I need. So it'll be f dotted with, I'm sorry, not f in this case, it's the curl of f. Let's get rid of that. It's the curl of f dotted with n dA. Just know that n means that you have to parameterize and do your cross product. That's what you're doing. Okay, so let's remind ourselves, how do we do the curl? Remember that the curl of a vector, a vector field, is the determinant of I, j, k, and then the second line are the partials. So it's the partial with respect to x, partial with respect to y, partial with respect to z, and we're doing the curl of f, so we go back to our f function. The I component is negative y squared, the j component is x, and the k component is z squared. And then we're going to evaluate this determinant. Remember that the middle row there, those are operators. Those are telling us that when we do the actual multiplication, we're going to end up taking the partials of whatever is in the bottom row. So let's go ahead and calculate the curl. Curl of f. Excuse me. So it's going to be a vector. If we eliminate the I row and the I column, we're going to get d dy of z squared. Well, that's 0. Minus d dz of x. That's also 0. So the first component is 0. If we eliminate the j row and the j column, we're going to get d dx of z squared. That's 0. Minus d dz of negative y squared. That's also 0. Remember to change your sign if you have something other than 0. And then the last one is the k row and k column. That one's actually going to give us something. So we get d dx of x, well that's 1, minus d dy of negative y squared. So the derivative of negative y squared with respect to y is negative 2y. We are subtracting that though, so it'll become plus 2y. So there's your curl. Now what it says to do is we're going to take the curl and we have to dot it with our normal and then do that with respect to dA. Now remember, A is going to be the area that this thing is going to take. It's going to be the domain that it takes to make up the region that we are bounding with C. So basically it looks like we're probably going to end up doing polar there. Now you can do this next part in two different ways. I've seen it done in multiple ways. We can either go ahead and parameterize this thing in polar right now and go ahead and do our cross products, or you could actually go ahead and parameterize this thing with the trivial parameters and do it that way, and then change it into polar at the end. I'm actually going to parameterize it using the trivial parameterization first, and then I'll show you what happens if we do it the other way. So we're going to parameterize this thing using the trivial parameterization. So that means we're going to go with x equals x, y is going to equal y, and z from this thing right here, because we're talking about that plane which is slicing down. If we solve that thing for z, z would be 2 minus y, so we're going to get z equals 2 minus y. That way all of our parameters are in terms of two variables. So we've got rx, which is the partial with respect to x. I did not write the full r out here. You can see it's this x, y, and 2 minus y. So rx is going to be 1, 0, 0. Partial with respect to y is going to be 0, 1, negative 1. So then we need to do the cross product. So we'll have rx cross ry. And let's see, rx cross ry here. If we eliminate the I row and column, we're going to get 0 minus 0. If we eliminate the j row and column, we're going to get negative 1 minus 0, but we have to change that sign, so it should become positive 1. And then if we eliminate the k row and column, we're going to get 1 minus 0, so that is 1. And that's good because, as you can see here, the z component is positive, which means that this thing is positively oriented. The flux of this is outward or upward in this case. Works either way. So that's a good thing. So the z component there being positive is good. Okay, so now we've got our cross, we've got our curl. We're going to go ahead and dot those and then do that over dA. Well, the nice thing is here, if you're really looking at this, the curl has the first two components of 0, so it doesn't really matter what my first two components of the cross are because they're going to be 0. So if I do the cross, and I'll write this out, if I do the dot product, if I write this out, so we're going to have the double integral. Let's go ahead and change the color. So we'll have the double integral over d of the curl, which is 0, 0, 1 plus 2y, dotted with the cross, 0, 1, 1, dA. So again, those first two components, when you dot them, are just 0. So really all we're going to get is the double integral of 1 plus 2y. Now we have to figure out what our region is. Well, in this case, this was sliced as a some kind of a cylindrical piece, so it looks circular. So I think the best thing to do again is to go with polar here, because that looks like that domain down there at the bottom was circular. So let's go ahead and take a look at what our domain is going to have to be if we change this thing. So x squared plus y squared equals 1 was the cylinder. So it looks like the radius is going to go from 0 to 1, and then of course it goes completely around, which means that theta will go from 0 to 2 pi. So we're going to have to go ahead and reparameterize this in terms of polar. So we know theta goes from 0 to 2 pi. We know r goes from 0 to 1. And then I'm going to have to change 1 plus 2y into terms of polar. Y in terms of polar, of course, is r sine theta. So this will be 1 plus 2r sine theta. Now I have reparameterized this thing right now, so it's not that it's already in polar. I have to reparameterize it, so I do need to include the r dr d theta. If I had chosen up here, and I'll go back and show you, I'm not going to do the full thing out, but if I had chosen up here to parameterize this thing in terms of polar, so maybe right here we could have said that x equals r cosine theta, y equals r sine theta, and then z here in this case would be, well, z was 2 minus y, right? So it's 2 minus r sine theta. If you had parameterized it that way and you'd done your cross product, you would not need to include the extra r that we have to include down here, because it already would be done in terms of polar. And if you want to try that, go ahead and try it. And you'll see that you're going to end up with exactly what we get in this next step, which is basically just distributing the r. So we get 0 to 2 pi, 0 to 1 for our integrals. Now we get r plus 2r squared sine theta, dr d theta. This is exactly what you would get if you had parameterized what I wrote in the purple and done the cross product that way. So you would not have to include the extra r. It would already be there because you parameterized it in terms of polar. That choice will be left up to you. Sometimes it's easier just to go with trivial and then change it later. Sometimes it's easier to go straight into the polar or whatever else you think you might need. All right, so let's go ahead and finish this one off. Scroll this up just a little bit. Won't need too much more room to do this. All right, so unfortunately we cannot separate all of this because you can't separate the r's from the thetas completely. So we're going to have to go ahead and just do it step by step. So the antiderivatives are going to be 1/2 r squared plus 2/3 r cubed sine of theta from 0 to 1. We still have our d theta and our 0 to 2 pi. So plugging in 1 is going to give us 1/2 plus 2/3 sine theta. Plugging in 0 gets rid of everything else. So we're good to there. Now we just have to take the antiderivatives here with respect to theta. So we're going to get 1/2 theta. And then the antiderivative of sine is negative, so it's going to be negative 2/3 cosine theta, and we'll evaluate that from 0 to 2 pi. So if I plug in 2 pi times 1/2 is pi. Plugging in 2 pi for cosine is 1, so that's going to be minus 2/3. And then minus, if I plug in 0 here for theta, now 1/2 times 0 is 0. Minus, plugging in 0 for cosine is 2/3, so that's minus 2/3. So what we get is, let's see, I'm going to have a negative 2/3 minus a minus 2/3, so that's plus. So we're just going to get out of this thing pi. Okay, and that was evaluating f dot dr, or figuring out this line integral using Stokes' theorem. So I did mention that I was going to say something about what it actually means. So basically what Stokes theorem is doing is it, because we're using the curl, what it's doing is it's actually taking this surface here and it's saying, okay, at every single point on this surface that this curve traverses, every point on this surface, it's associated with some kind of a curl. Now, if you remember what the curl was the rotation, or the tendency for this thing to rotate in or out of the surface. So at this point right here, maybe the curl is going in, a certain direction, so it's going that way. That's really hard to see. Let's try a different color. Let's go with blue. It's doing this. And then maybe up here it's doing this, but maybe up here it's actually going the other way. And then maybe up here it's going this direction. But as this thing goes around it counterclockwise, what is the curl doing? Maybe at some places the curl isn't doing anything. Maybe it's just it has no curl. But then as you go around this direction, what's the curl doing? As you go around this direction, what's the curl doing? It's every single point on the surface. It's accounting for what is the curl doing on this thing, which is basically the same thing in 3 dimensions as figuring out what the line integral would be around that surface. All right, we're going to come back and we'll do example 2. Okay, example 2 says use Stokes theorem to evaluate the double integral over S of the curl of f dot ds. So here's one of the things that you're looking for when you're doing these problems. It says to use Stokes theorem. So that means if it's giving you one thing, it wants you to use the other one. Otherwise, you're just evaluating the double integral of the curl dot ds. It's not really using Stokes theorem. But since it says use Stokes theorem, because they're telling us to do the double integral, they actually want us to use the line integral instead. So we actually need to make sure that we remember that this is the same as the line integral over c of f dot dr. That's what we're going to use. So if it tells you to do the line integral, then it wants you to use the curl portion to do it, if it says to use Stokes theorem. And as you can see here, by looking at your force vector, doing the curl of that would probably get pretty messy, because you're taking partial derivatives of things like x squared, e to the yz, and all that kind of stuff. It's going to get a little bit messy to do. So what they're telling us to do is to use the other method. It's when they don't tell you a method, that's when it becomes a little bit more challenging, and it just says to find this. Then you have to figure out which one is going to be the most convenient. And sometimes you start with one and realize this is just too messy, let me try the other way. And unfortunately that can take some time. But in this case it is telling us which way to use. So what we have here is we have this vector field, which is looks like it is through the hemisphere, x squared plus y squared plus z squared equals 4, and z is, I'm not sure if you guys can read that, it's supposed to say greater than or equal to 0, I believe. It's kind of messy on mine. I hope it's not that bad on your sheet there. Yeah, maybe it's just greater than 0. It won't matter in that case, but that's definitely z is greater than 0. Okay, and it says it has it's oriented upward, which should make some sense. So let's go ahead and sketch this just real quick to see what it looks like. Whoops. Excuse me. So we're looking at, let's see, it says the upper, yeah, it's the hemisphere greater than 0, so it's the upper part of the hemisphere. So let's see how well I can draw this. So you're going to have some kind of a circular hemisphere type of thing going on like this, sitting on the XY plane, close enough I guess, upwardly oriented. So that means that the vector field is, we want the vectors to be going this direction, upwardly oriented, okay? And it does need to have a positive orientation. So that means that we have to go around C in that direction right there. Alright, so let's go ahead and take a look at this. So remember that the line integral over C of f dot dr, remember that dr is just the derivative and f has to be parameterized. So this is the same thing as the integral from a to b of our vector field of r of t dotted with r prime of t dt. And that's how you do the line integral. So what we need to do is we need to parameterize our hemisphere here. So let's see, r of t is going to be defined. Well, it's definitely spherical because it says hemisphere, so let's go with, well, we don't have to go with spherical because we're just doing this around the line integral, so it looks like we can just go polar on this thing. And we are talking about just the ring because we're talking about the c value, so the radius here is going to be 2 because it tells us that the hemisphere here has 4 on the outside there, so that's r squared. So we're going to have our r vector as 2 cosine theta, 2 sine theta, and then z in this case is 0 because it is sitting on the xy plane. So then we're going to need r prime of t, and we will parameterize f in just a second. So we're going to need r prime of t, which is going to be negative 2 sine theta, 2 cosine theta, and then 0. Alright, so now we're going to need to parameterize f. And now we can go ahead and dot these things. So let's parameterize f. So if I were to plug in, excuse me, if I were to plug in 2 cosine theta for x, that's going to give me 4 cosine squared, and then it's times e to the yz. So it's going to be e to the 2 sine theta times 0. The good thing there is that's e to the 0. E to the 0 is just 1. So really all I get out of parameterizing this first piece right here is going to be the 4 cosine squared theta. Okay, I'm hoping you guys followed that. If I plug in the y and the z, 2 sine theta and 0 into the exponent of e, it just gives me 0 in the exponent, so e to the 0 of course is 1. So all I'm left with is the 4 cosine squared theta. Alright, let's try the same thing here with the second component. So that's going to be 4 sine squared theta, and then it's got to have e to the xz, but again the z part is 0, so it's e to the 0, so that's 1. So I'm going to get 4 sine squared theta. And then the last component here says I've got a z squared in it, and z of course is 0, so it doesn't even matter what the exponent of the e here is, so it's going to be 0. Okay, so that is my f parameterized. So now what we have to do is we have to dot those. So if you look at what we've got is we've got f of r of t, and then I'm going to dot it with the r prime of t right above. So the z component is going to be 0. It's going to go away. So let's go ahead and write this out. So we're going to have the integral from 0 to 2 pi, because that's what the c does, the c part. And we'll just label this real quick here. This was c. That's the curve right there that we're talking about. So let's see, if I dot these things, I'm going to get negative 8 sine theta cosine squared theta. And then if I dot the second one, I'm going to get plus 8 cosine theta sine squared theta. And then again, z part is gone. And this is d theta. Alright, so in order to do this, we're pretty much going to want to, I think, probably separate this into 2 separate integrals. Otherwise, the math is going to get really messy and it's going to be hard to keep track of. So, if we were to do this, let's separate it. 2 separate integrals, 0 to 2 pi of negative 8 sine theta cosine squared theta d theta plus integral 0 to 2 pi of 8 cosine theta sine squared theta d theta. And the reason I want to separate these is because we're going to have to do a u substitution on both of them, and in each case the u is a different value, so it just makes it easier to see, I believe, to do it this way. In the first one, we're going to have to let u equal cosine. So if u is cosine of theta, du is going to be negative sine theta d theta. So d theta is du over negative sine theta. And here's the good news on this one. This is really going to make things nice. I don't actually have to go ahead and redo this whole thing. Here's why. Excuse me. If I change the bounds, if I plug 0 in for theta, that's going to give me out cosine of 0, which is 1. So my lower bound becomes 1 for u. If I plug 2 pi in, cosine of 2 pi is also 1. I don't really care now what I'm taking the integral of, because my integral is going from 1 to 1. So this doesn't matter, because the integral from 1 to 1 is just 0. That is wonderful. Don't have to worry about doing all the math there. Let's go to the second one. If I let u equal sine of theta, that means du equals cosine theta d theta. So d theta equals du over cosine theta. Once again, I'm going to go ahead and change the bounds. So if I change the bounds, if I plug 0 in for theta, I get out 0. If I plug 2 pi in for theta, I get out 0. Once again, it doesn't matter what I had here, because I'm going to go from 0 to 0 on my integral, which just means I get 0. So ultimately what this thing gives us is 0. And all that that really means is, remember that we're talking about we're talking about what's going through this surface, or how the curl is acting on that surface through this, here, let me go ahead and shade this in, through this region right here. It's what's really happening right there. How's the curl reacting? So what that's telling me is that there's an equal amount of curl that's going in one direction, that's going in the other direction, or basically the flux of this thing is balancing out. Whatever's going into that surface is coming out exactly the same way, and the curl is affecting it in that specific manner. Here's kind of the whole idea of what's happening here. Notice what we didn't use at all, other than to parameterize our, other than to get our bounds of, to parameterize. The only thing that we used that hemisphere for was to get the 2 as the outer bound for the parameterization. Otherwise, we never used the hemisphere part at all. And actually, we didn't technically even use the hemisphere, because just that the hemisphere was projected down into that yellow domain down there. So we really didn't use the surface of the hemisphere whatsoever in this case. And that's the ultimate idea. So somebody actually once showed me that the idea was, if you have some kind of a surface, and we're just going to make this some kind of a circular surface, and you've got something going through the surface. Now, he used the idea of rain, and so I'll just make like a whole bunch of raindrops coming down here through the surface. Whatever this is, the rain is coming into this surface. It doesn't really make any difference what we have below or above the surface, as long as it is bounded by the actual surface, the ring itself. So I could have some kind of a cone or something like that underneath the surface. And I think the way he put it was, if a gallon of water falls through this ring, it doesn't matter what's underneath to catch it. It's still going to be a gallon of water falling through the surface. So think of this surface here as being like some kind of a net. Okay, maybe it's very porous, maybe it's not, but it's some kind of a net. If I have a gallon of water fall through the surface, maybe I'm going to change instead. Maybe I'll make this cylindrical under here. Okay, that doesn't make any difference as long as it once again is bounded by the curve. If a gallon of water fell through when it was a cone underneath, it's still a gallon of water that's going to fall through if it's a cylinder. And again, all of this is based upon the curl that's occurring at that particular net. What's happening with the vector field as it hits based upon the curl. So we never use the surface at all, and it's not going to make any difference using Stokes theorem what the surface is, because it's really only what is happening at that net right there. So the surface part of this doesn't matter. That's kind of the ultimate takeaway from this. And hopefully that'll make some kind of sense and help you to figure out what it is that we're actually calculating as we go forward.